In this section, we're going to talk about frequency analysis of noise. So to understand noise, we need information about both its pressure levels as well as its frequency characteristics. So frequency matters because humans hear different frequencies at different volumes. So quantitative measurements must be corrected for the perceived intensity. So different weighting scales have been developed to try to take these differences into account. And largely because of this, many industrial codes and regulations are based on this idea and are therefore expressed in terms of specific frequencies. So humans can typically hear frequencies from about 20 hertz to about 20 kilohertz. This is a lower range for older individuals, or particularly, or also those with hearing loss. And as we age, we start to lose our hearing perception in the high frequencies first. But in general, we can think that the frequency range that we're talking about here is about 20 hertz to 20 kilohertz. So to deal with acoustic frequencies that become bothersome to humans, we use actually a geometric scale where frequency bands are used. So this is different from the logarithmic scale or the dB scale used for sound pressure levels. So bands are defined by both a lower frequency, or FL, and an upper frequency, or FU. And then the bandwidth is the difference between this lower and upper frequency in the band. So bandwidth, or BW, is FU minus FL. And the bands are named for their center frequency, which is defined as the square root of FL FU. So it's not actually the average, but it is a geometric mean, where the property, with this property that the ratio of FC over FL is equal to the ratio of FU over FC. So each band follows a common rule, which is that FU over FL is equal to 2 to the exponent k. So the value of k determines the type of band. There are different types of commonly used frequency bands. And in general, for the nth band, f of n plus 1 divided by fn is equal to 2 to the exponent k. So this is shown for 4 bands below. So you can see the nominally, or in absolute terms, the distance between the bands is not constant, but it follows this relationship that we just explained here. So the center frequency for each band is then FC is equal to the square root of FL FU, which is the square root of FL times 2 to the exponent KFL, which is equal to the square root of 2 to the exponent k times FL. Or FL is equal to 1 over the square root of 2k, or 2 to the exponent k, FC. And similarly, FU is equal to the square root of 2 to the exponent k, FC. So the bandwidth, which we defined as FU minus FL, is equal to the square root of 2 to the exponent k, FC, minus 1 over the square root of 2 to the exponent k, FC, which we can write as shown here. So for a given k, the bandwidth of a given band is a fixed percentage of the center frequency of that band. So that means, because of this, these are known as percentage bands. If k is equal to 1, then we get something called an octave band. So in this case, FU over FL is equal to 2, and the upper frequency is twice the lower one. So these bands are known as octave bands. And we can find from our previous equation that the bandwidth is equal to the square root of 2 minus 1 over the square root of 2 times FC. So the bandwidth is approximately equal to 0.707 of the center frequency FC. So most work with octave bands uses standardized bands, as shown in the table on the next slide. These bands are relatively crude, and more refinement can be obtained if we used fractional octave bands, which we will talk about in a moment. So these are, this is a table showing the lower frequency, center frequency, and upper frequency for these full octave bands. So for example, if you look at this one here would be called the 1000 hertz frequency band, and its bandwidth would be from, it would hold all frequencies from 707 hertz up to 1414 hertz. A very common type of band is called a 1/3 octave band. So for this, we set K is equal to 1/3 in our previous equation. So now FU over FL is equal to 2 to the power of 1 over 3, which is equal to the cubed root of 2, or 1.26. So here the upper frequency is only 26% larger than the lower, and in terms of the center frequency, we get that FL is approximately 0.89 of FC, and FU is 1.12 times FC. So then the bandwidth is this sixth root of 2 minus 1 over the sixth root of 2 times FC, which is approximately 0.23 times FC. So these 1/3 bands provide a higher level of detail when characterizing noise. And there's a table shown in the notes with standard 1/3 octave bands showing their center frequency as well as their lower and upper frequency for bands going from about 22 hertz up to 22,000 hertz. Okay, so next we want to talk about psychoacoustics and weighting networks. So often in acoustics, the actual RMS pressure values that are measured must be modified based on their frequency. They're modified using a weighting system. And so this is because human sensitivity to sound is frequency dependent, so we give different weights to different frequencies. And the study of how people respond to sound or how people perceive sound is known as psychoacoustics. So to account for perceived sound levels, different weighting scales have been developed. A weighting scale is the most common weighting scale in acoustics, and it most closely approximates the frequency response of human hearing. The rates of hearing loss also tend to follow the A scale as well, and one sort of component of this is that one can tolerate higher levels of low frequency noise for a longer period of time without impairment. So for these reasons, the A weighting scale is by far the most predominantly used in noise measurement and control. And most electronic sound measurement equipment are able to determine A weighting sound pressure levels directly. Another common scale is the C weighting scale, which is relatively flat in the frequency range. And so it provides a good baseline for comparison. And there's also a linear weighting scale, which is just the straight SPLs with no weighting adjustments. So this shows the SPL corrections for different weighting scales. Here showing the A weighting scale. There's also a B weighting scale in between, and then the C weighting scale, which you can see is very flat across the frequency range. So here we're showing the relative response in dB versus the frequency, and the frequency here is shown on a logarithmic scale from about 20 hertz up to 20 kilohertz. And there's a large table in the notes that shows the weighting scale correction factors for both octave and 1/3 octave bands for these three different weighting scales, A, B, and C weighting. So you can take a look at that to understand how these weighting scales work. Okay, so the last section that we want to cover is called fluctuating noise levels. So in most situations, noise constantly is fluctuating. It's not a constant level. It's typically varying continuously. So the type of noise and the reason that we're interested in measuring it will influence how we deal with these fluctuating noise levels. We can use short-term measurements, we can use LEQ levels, we can use equivalent sound levels. All of these can be used to quantify fluctuating noise levels. So short-term measurements, just as the name implies, it's a way to determine how loud is the sound right now, so over a short period of time. So sound level meters can measure a running time average of the square of the pressure signal, so basically proportional to the energy content of the acoustic wave in either fast or slow modes. A fast measurement may be a period of 100 to 125 milliseconds, while a slow mode could be between half a second to up to a second. And basically it quantifies some average of the noise during that period of time. Slow measurements are more stable, and fast measurements are more sensitive to rapidly changing noise levels. We can also use peak measurements. So the peak sound measurement is the highest instantaneous pressure level experienced during the measurement time. So this is different from the highest levels measured in the fast or slow modes for the sound pressure level meter, because those are averaged over a period of time. This would be just the actual peak measurement. And peak measurements can be more than 20 dB greater than these averaged values. So next we can talk about LX levels. So for characterizing the long-term variation in sound pressure levels, we may not want to describe the entire sound history, which would be something like what is shown in this figure here. But instead we might only care about the percentage of time that the SPL exceeds a certain level. So to do this, we can use LX levels. So LX is typically on an A-weighted SPL that is exceeded a certain percentage of time, as shown here. So basically, L1, this is some value in SPL that is exceeded 1% of the time. L5 would be some value in SPL that is exceeded 5% of the time. L50 would be some value in SPL that is exceeded, and these are SPLA typically, that is exceeded 50% of the time. And these are generally defined for periods of 15 minutes, 1 hour, or 24 hours. So last we can talk about equivalent sound levels, or LEQ, which is defined as a constant sound level that has the same acoustic energy of the fluctuating sound over the same period of time. So it can be written as 10 log of P average squared divided by P ref squared, which is, if we just plug in our definition for this P average, and here we're using an A-weighted P. So then LEQ is 10 log of 1 over T, integral from 0 to T of PA over P ref squared, where T is the period of interest and PA is the A-weighted sound pressure. So the A-weighted sound pressure can be found from the A-weighted SPL using our previous definition. So PA over P ref squared is equal to 10 to the exponent SPL over 10. In some cases, the sound fluctuations can be considered as a constant SPL over certain time periods. And in those cases, we would consider, so SPL would be essentially defined as piecewise, where it's equal to SPL1 for F1, SPL2 for F2, SPLN for Fn, where Fi here is the fraction of the time interval t over which the sound pressure level is SPLI. So the sum of all these Fi's should equal 1 because it is just the portion of the interval of time. So in this situation where SPL is equal to SPL1 for F1, SPL2 for F2, up to SPLN for Fn, then we can write this LEQ, this equivalent sound level, as 10 log 10 of 1 over T, integral from 0 to T of PA over P ref squared, which we can then write in terms of these F1T, F2T, these fractions of time. And we can cancel out the T in all of these and see that we get this expression here. And for each of these P1 over P ref squareds, we can rewrite that as 10 to the exponent SPL 1 over 10 up to 10 to the exponent SPL n over 10. So what we get is that LEQ is equal to 10 log of the sum of Fi times 10 to the exponent SPLI over 10. Where again, Fi is the fraction of the total time spent at the sound pressure level SPLI. So this brings us to the end of the course content. So we'll just do a few examples related to sound and acoustics, and then that will wrap up our course.